call. No. I just hid my view. Now I can't find where my screen is so that I can do the mute and all that stuff.
Take your cursor, very lightly scroll it down over that little screen part.
We'll get rolling with some intros here. Welcome, my name's Bernie Miscible. I'm the Director of Health and Safety at the FTI. I've been practicing industrial hygiene for going on 26 years now. I think I recognize most of the names and faces. We might have seen each other before in some fashion or format. This class that we're going to be doing today is physical and chemical properties of hazardous materials. So we're going to look at the basic ways that chemicals behave. And this is going to be a benefit because we're going to look at it, you know, in relation to how we protect workers that work around chemicals. And it just so happens to be that, you know, IOPA team members work around a lot of chemicals. Whether you're a glazer, painter, floor cover, wallpaper, you know, drywall finisher, doesn't matter. There are a lot of chemicals there. And these things behave differently. And sometimes in the environment that you're using them in can change their behavior. So it's good for us to understand that. Now, if you are a trainer, this is going to help give you a better platform if you're doing any kind of health and safety classes that relate to chemicals in any way. Does anybody here teach any classes that they think might have chemicals as part of their curriculum? So what classes might you teach that have chemicals as part of something in the class? Anybody teach HAZWOPER?
Yeah, we do, Bernie.
Yep. How about respirators?
Yep.
All right.
I'm thinking basic, just your regular painting classes.
Yep. Yeah. All right. Good. So that's going to help, you know, understand that material better and why it's important, you know, to protect us from chemicals, how they behave, things like that. Also, if you've got any responsibility at your local or district council for health and safety of any kind, this is going to help give you a better foundation for understanding chemical behavior out in the field. And we're going to talk about that as we go through some of this stuff. With that said, I'd just like to know who we got on here today for the class. We got you know, a small enough group where we can go through. If you want to just introduce yourself, where you're from, and why you decided to take this class, would be great.
Yeah, sure. My name is Eric Redding. I'm the Director of Training at DC 35. And I just wanted to join in. I wanted to learn a little bit more about the class, see what was going on.
Great. Oh yeah, Eric, hello. One of my district council people.
Good to see you, Bernie.
Yeah. All right, who else we got?
Okay. Ray Spagaforno, Apprenticeship Training Coordinator with District Council 4. I'm in our Portland facility. We're out of Buffalo, New York. My director signed me up for this class so that we have more trained staff on hand for instructional purposes.
Great, welcome.
Matt Naska, also out of DC4. And we're all signed up for the same reasons over here at DC4, just broaden our knowledge.
Great, welcome.
Thank you.
Brandon Johnson from District Council 58, Decatur, Illinois. Same thing. Just here to further our knowledge.
Okay, welcome. What else we got?
And Bernie, that's basically it for right now. So Kevin Harned's on, but he's supposed to be helping Terry Mitchell and a couple other people in his office get on. So that's what we're working with right now.
Okay.
We got two other guys struggling here in the building trying to get on.
All right, well, they can join us when they'd like, and maybe just say hello and they hop on. That would be fine. A couple materials that we'll have for this is there's going to be a manual that was sent to you, PDF, that's basically the written word that I developed for these slides. And they included a group activity, a small group activity at the end, which we're going to go through. And then a pocket guide is going to be, you know, required for this course as well. And then of course the slides that we have. This module itself can be related, or class itself can be, modular and related to a lot of other classes. I initially designed it for a 40-hour HAZWOPER class. Is anybody here familiar with HAZWOPER, what that rule is and what the courses are? Now, so HAZWOPER, right, it's a 1910 120, the Hazardous Waste Operations and Emergency Response Standard. It's one of the best OSHA health and safety standards, I think, that is out there. It's been tested in court many times. It's held up many times. It was enacted at the end of the 80s in reference to, all of our hazardous waste sites, and really what the, I guess, linchpin for its development was what happened in Bhopal with the diisocyanate accident that happened over there, and ultimately ended up killing, upwards of 20,000 people. And this is a course too that we can teach. I know that CPWR teaches it. We get funding technically through the CPWR grant program that's associated with NIHS to do HAZWOPER classes. And this is one of the things that I developed a while ago. And then I use it in a bunch of areas. So with that said, we're going to go through it. And, I'd love to do this face-to-face, but we're not. If you've got any comments, questions, please, bring it up when we're going through. We'll try to make it as interactive as we can. And my goal is not just to teach, these principles of hazardous materials. It is to also relate it to work and how we're going to protect members out on the job with understanding this stuff better. That's the goal. All right, well, that said, let's get rolling here. So after this course, we're going to be able to define what a property is and differentiate it between a physical and a chemical property. List and describe at least 6 physical and chemical properties of hazardous materials, and explain why knowing this can help you stay safe. Define the following types of radiation: alpha, beta, gamma, and neutron, and state which has the greatest health impact. And then use the pocket guide to find material, physical, and chemical properties. And I gotta say, this handy book here, although it does not fit in my pocket, is probably one of the most used resources that I have gone to in my 26-year career of practicing industrial hygiene. It's got a lot of stuff in it. And I'm sure, if you've taught anything from respirators to HazCom, you probably, reference this book quite a bit. With that said, we do have radiation up here because those do fall into this category of physical and chemical properties. I am going to be teaching 2 separate classes, one on the basics of radiological materials and the other one on health effects. They kind of go together. And we're gonna, I think, teach that in February. The calendar should be out soon, I guess, with those. And, if you ever worked or work at a Department of Energy site, if you work at a shipyard, if you work, with radiological sources of any kind, because we do have some that we use in construction, this would be a good class to take. And also, if you teach any HAZWOPER classes, covering rad is part of HAZWOPER, although it's small, but it's still a part of it that you have to talk about, and it would give you a little bit more comfort in doing that as well. And this is something that we thought could maybe be a benefit to our trainers during this time when we're all on Zoom and not doing the normal stuff that we do. So anyway, little plug for that. So hazardous materials have observable and measurable properties that enable us to identify them. An example here is I got a car. This Buick, you've got a make for a car, you've got different models, right? Year, color. So these are all different properties that describe that vehicle, and it makes it unique and identifiable. And we can measure these things, observe them, etc. And the same is true for chemicals. So physical properties and chemicals properties are 2 types of distinguishing phenomena for chemicals. So a physical property is something that we can observe without changing that substance into something different, right? So we look at it, we can measure it, we can observe it, but it's not going to actually change that chemical. As opposed to a chemical property where the characteristic involves the hazardous material's interaction with another substance, and it could change its chemical makeup. So what am I talking about with this stuff? So for physical ones, we've got examples of hardness, right? And I don't know if you remember back to your high school geology, where we had that hardness meter with the different marking tools you'd have to test hardness of rocks on and stuff like that. A melting point, so what temperature something changes from a solid to a liquid. its color, texture, right? How it feels. Is it abrasive? Is it smooth? And density. What mass is it per certain unit volume? So these are all things that we can look at, and it's not going to change, what that chemical is, as opposed to chemical properties. So these are things like flammability, reactivity, ionization potential, which relates to air monitoring. We need to know about a chemical's ionization potential if we use a photoionization detector, heat of combustion, and toxicity. So these are some examples of things where, it's their property of interacting with something else that's actually going to change then what that is. If you light a chemical on fire, it's no longer that chemical, which is one of the problems of being a firefighter. It's a pretty toxic work because as they're fighting that fire, it's an uncontrolled chemistry experiment. What's going on in that building? I mean, imagine all the building materials that you work with as an IUPA team member, and imagine lighting all that stuff on fire. Right? It's changing what those chemicals are now, and it's changing into something else. And we have some ideas of what those groups of chemicals would be in a circumstance like that, but we wouldn't know everything. And that's why one of the reasons we see firefighters have such terrible incidents of cancers and other debilitating long-term chronic diseases that are caused by chemicals. All right, so chemicals are found in one of 4 states or phases of matter. We've got solid, liquid, gas, and plasma. And I'm mainly going to talk about the first 3. Plasma is it's gas-like, but in plasma, all the atoms there are positively charged. Whereas in normal gases, you have positive and negatively charged gas molecules or atoms in equal amounts. So you have a neutral charge to that gas, but plasma is a little something different. And we're not going to get into discussing it now because it doesn't relate much to worker health and safety unless you're in some very specific fields. But these first 3 absolutely do. So each state can have different types or subcategories, right? Can anyone name some of them? So let's think about solids. So we identify solids as a state of matter or phase. How many subcategories do solids have? Think about what you might be producing if you're sanding something. Anybody got any examples?
Like a dust or something?
Yeah. Dust is one good one. What other kinds of solids do you probably teach classes about that are pretty harmful?
Paints?
Paints. And paints can be both a solid, I guess, and a gas, right? Or in a liquid, depending upon what drying, I guess, state it's in.
I guess it's all 3.
Yeah, it's all 3, right? And each one of those, depending upon what state it's in, is going to have the ability to affect a worker in a different way. How about asbestos? Anybody teach asbestos classes? Right, so fibers are an example. So here we got some that I listed up here. So solids, we can have aerosols, which an aerosol captures a lot of stuff. Actually, an aerosol is all those other examples there. And an aerosol is a suspended solid or liquid in a fluid medium. And the fluid medium in this case I'm talking about is air, but you can have an aerosol of a solid or liquid suspended in a liquid. But an aerosol, so you've probably heard this a lot with COVID, right? Is it aerosol generating procedure? Is it aerosol transmissible? Things like that. Dust is an example somebody gave. Fibers, fumes. What's a fume? Does anybody know what a fume is?
It's gas made out of like metal particles.
Yeah, good. And I'm pretty particular about talking about some of these definitions because it's important to make sure that we're going to do the right thing to protect members about it. You've probably heard this a lot. You've probably heard it happen on the news a lot where people talk about the fumes at the gas pump, right? Oh, those fumes are so bad when I'm pumping gas. They're not fumes. What are they? Vapor. Right. Yeah, so a fume is, you're using an incredible temperature to heat up very quickly metal, and it's going to volatilize it and create a vapor out of that metal. And when that happens, as soon as it gets away from the surface, it cools. And when it cools, it creates these really nice, almost perfectly spherical, same-sized particles. And that's what that fume is. And, you know, to my knowledge, I think IUPAT members, we offer certifications in welding, right? Right, so our members might be around welding fume, and that can change as far as the hazard, depending upon what you're welding on, what the rods are, what type of welding, what area you're welding in, right? If it's a confined or an enclosed space, or maybe outdoors, it's going to be a different hazard. And also if you're doing any high, you know, heat cutting, in some instances, you know, grinding can produce fume too, but typically not. Then we've got liquid, and we can have aerosol again, as I mentioned. So if you're doing like any hydroblasting, high pressure washing, anything like that, you're going to be creating an aerosol. It's a mist. It's basically a liquid suspended in air. You can have gels, adhesives as well, are examples of liquids. And then gases, and we're going to throw vapors in this. So a vapor is a gaseous form of a liquid, and we're going to cover that a little bit more as we get into the slides here. But I've got some common gases here: acetylene, if anybody uses any acetylene in their work. You know, oxygen, carbon monoxide, usually a very common toxic gas that's found on construction sites or associated with construction. And nitrogen, which is it's a non-reactive gas, and we use it for a lot of different things, but it just so happens it can displace oxygen and lead to asphyxiation for workers. So there's some examples of gases, and I'm sure you've got other examples of things that you work with. So each phase of matter has a unique property, right? So gases, it's an undefined size, shape, or coverage area. But what it's going to do is once you release a gas into an environment, it's going to take the shape of that environment, and it's going to fill all the space. So if I had my kombucha tea bottle here, like let's say if this was a gas, and I took the cap off and I put it in this room, that gas is going to escape the bottle. The molecules are going to touch every surface in here, the ceiling, the floor, all the walls, and it's going to fill that space. It's going to take the shape of my space. If I had slanted ceilings and stuff like that, it's going to take that shape. And this is important to understand because that yields a different concentration depending upon how much gas you've got and what kind of room it's in or environment. For instance, let's take this, you know, this gas bottle example here, and I open that up in my room. It's going to have some concentration, right? What happens if I took that same gas bottle and brought it into a gymnasium at a high school, and I open that up? What's going to have the higher concentration of gas? My office room here or a high school gymnasium?
Your office.
Yeah, right. So this is important stuff, right? So now if you've got somebody working in a confined space, a tank, you know, a closeted area, a enclosed space, which doesn't fit the definition of a confined space, but let me tell you, if you're using volatile chemicals in there, it's going to cause an issue. So this is a way that we can use these properties to understand how it's going to affect a worker. So these are things you should be looking at. And we can find this information on safety data sheets, but sometimes we have to go a little bit deeper into resources to find out what some of these properties are, if you're the one who's going to be responsible for doing a risk assessment or some kind of a job hazard or safety analysis for workers. And I'll make the caveat, employers always have the ultimate responsibility for doing that for their employees, but it's nice as a union to be able to have an understanding of what's going on so we can at least provide another layer of protection for our members, right? Liquids, they've got a fixed volume. So, you know, this is a, where the hell is it here? A 12-ounce bottle. It's never going to be anything other than a 12 ounces of liquid that I can fit in there. So it's got a fixed volume. It's going to take the shape of whatever bottle or container it's in, whether it's a square, it's a cylinder, it's a globe, whatever. And the surface area can change, right? So if you imagine a 5-gallon bucket of paint, right? It's got a defined surface area. What happens if you spilt that bucket out on a driveway? That surface area now changes quite a bit, right? And that has a lot of impact on whether or not something can be volatile and vaporize. The more surface area a liquid has, the more likely it's going to volatilize and get up in the air, which can affect workers. And then finally, we've got solids. So these things have a fixed size, shape, and surface area. The only way that's going to change is if you mechanically damage it somehow. And how do we mechanically damage or alter solids in our work? What are some examples of doing that? About sanding, maybe, cutting, sawing, drilling, rasping, all that stuff, right, is going to physically alter solids and its shape and its size, surface area, etc. And some of those methods are worse than others, right? So hand scraping is going to produce less finely divided particles as opposed to sanding, right? And so this graphic is pretty important because matter can change phases, and they're going to sort of be somewhat going on constantly. And then we can affect that based on things that we can do in the environment. So gases are going to go between, a liquid and a vapor phase and then back. We'll ignore plasma for now, but solids, they can sublimate, and we'll talk about what sublimation is in a little bit. And then gases can be redeposited to a solid. Solids can melt, turn into a liquid, and liquids can freeze. And these things can be going on sometimes, at the same time. And one phase will be more prominent than another phase. For instance, if it's cold out, you might have something starting to freeze from a liquid, but you still might have some liquid behind, and you might have more solid, et cetera. Okay. All right, so these are some of the physical and chemical properties that we're going to look at today. We'll get through these and then we'll get into our activity. There's a lot more out there than this, but these are some of the ones that are most typically associated with protecting workers. So we've got melting point, pH, vapor and gas density, vapor pressure, boiling point, flash point, and then flammable limits. All right, so melting and freezing point, this is a temperature at which a material is going to change from a liquid to a solid to a liquid, or go back, right, from a liquid to a solid. These are all defined, and these are typically given for a pure substance. So if I look up, a melting point in this pocket guide for a chemical, it's going to be for that chemical in a pure substance. If it's contaminated somehow, it's going to change. That's one of the reasons why we throw, so for those of us up in New England or in New York, especially in Buffalo, why do you throw salt or sand on an icy driveway?
You don't bust your butt.
Yeah, that's right. I'm not very good at ice skating. We're going to change the melting point of that solid, which is water at that point, right? By throwing that stuff on there. So we can manipulate, some stuff around us. Vapor pressure is a measure of a liquid's ability to evaporate or give off vapors and have those vapors spread out. So every liquid has a vapor pressure, and vapors are always escaping. Some are escaping faster, some are escaping slower. It really depends on the liquid. Also, we can change that up by adding heat or taking away heat. And when you look up a vapor pressure, they're always for a specifically defined temperature. In this pocket guide, it's room temperature, I think 76 degrees Fahrenheit. But you can look at vapor pressures for different temperatures if you look in a chemical dictionary or things like that, or you look up specifics on a chemical in a register for chemicals. And this is a really important one to grasp for worker protection, because vapor pressure has to do with a lot of different stuff that can harm workers. They're gonna, they vary widely. Here I've got an example of propane, which is 6,384 millimeters of mercury, down to sulfuric acid, which is 0.001 millimeters of mercury. This is a huge difference. And down here I've got a scale, and 760 millimeters of mercury equals 1 atmosphere. And typically what you're going to see once you have chemicals that are like this, if they're in liquid form, they're going to present their vapor pressure in atmospheres to make a more usable number so that we don't have thousands of millimeters of mercury presented. And they're going to do that in the pocket guide. So if you ever see an atmosphere for a vapor pressure, it's probably going to be a liquefied gas, right? Like propane or butane is. And this is important to understand because that has with it other connotations. So if it's a liquefied gas, you've probably got some other health hazards with it. It's going to be cold upon release. So if you spill a liquefied gas on you, what's going to happen?
Frost burn.
Yeah, that's right. You're going to get a frost burn due to cold. Also, that's something that you don't really want to expose to heat if you're not venting it, right? There's a lot of unfortunate examples of enclosed liquefied gases that were subjected to heat and fires, and you've had massive explosions. With that said, just because something has a low vapor pressure like sulfuric acid does not mean it's not going to be an airborne hazard. It depends really how much of it is you have that's maybe spilled or that you're exposing the worker to, what the surface area is. But typically these things aren't going to get up into the air in most circumstances just through vapor pressure to harm a worker. I can tell you by experience, I have to be right above an open container of sulfuric acid for me to smell the vapors. Now, we're not supposed to ever use our senses to detect chemicals, but nonetheless, we don't ignore them. And I can tell you that once I detected sulfuric acid vapors, I did not stay in that room. But things can change that vapor pressure if it was subjected to heat, if you had a spill of this stuff, if you're mixing it. So, if you're adding any chemicals, let's say if you're mixing paints, right? By agitating that mixture, you're actually going to instigate the vapor pressure of that material. And so you're going to likely be generating more of that vapor up into the air. So these are all things that are going to work, in conjunction to affect a worker's health and safety. What else? Where am I going here? Boiling point is connected to vapor pressure. So a boiling point is that temperature of a substance at which the vapor pressure of the liquid equals the environmental pressure surrounding that liquid. So, if I'm boiling water from, an open pot, let's say on the stove, that's being compared to the environmental pressure around that pot that I've got on my kitchen stove. And that can change. I can boil water outside, right, on a fire, right outside my door, and that's not going to really change the environmental pressure. However, if I hike up to the top of, Mount Kilimanjaro, I'm going to have a different altitude there, right? Or if I'm boiling water outside in Boulder, Colorado, it's going to boil more quicker. So we can, change the boiling point depending upon what the environmental pressure is around that material that's boiling. And this is important because if you're heating, a liquid up, you're going to be volatilizing it and you're going to be pushing that stuff out into air. Any comments or questions on the stuff we covered so far? Okay. Next, we're going to talk about persistence. Refers to how long a material can remain in an area upon release. And for those of you who might have taken the PCB awareness course that I put on with Wayne Cummings and Jim McAllister, either in the summer or during the winter, PCBs are a very persistent chemical, unfortunately. So this is a property of the chemical for how long it's going to stick around once it's released out of its container. Persistent materials don't evaporate within 24 hours. They're going to stay there, sometimes for days, sometimes in the case of PCBs for years, decades. And the non-persistent ones are going to evaporate in less than 24 hours. Does anybody have an example of what groups of chemicals would be considered persistent chemicals and what might be non-persistent chemicals?
Asbestos lasts forever.
Yeah, yep. Asbestos lasts forever, yep.
Lead would be another one.
Yeah, lead's persistent.
He took mine.
What was that example?
I said he took mine. I was gonna say lead.
How about pesticides? Has anybody done any for farming ever or gardening? And you maybe put some pesticides down. Those chemicals are expensive and they're designed to kill, pests that are going to attack our crops. So probably wouldn't be a good property if those things just evaporated right away, right? So those things are going to stick around for a long time, for days to weeks before they evaporate or break down. Weapons of mass destruction, unfortunately, those things are very persistent. Those things stick around for a while.
Oh, uranium.
Yeah, uranium, and that's persistent for another reason. We'll get into that a little bit. How about some of the painting materials that you might use that are non-persistent? Do you have any examples? Some of the chemicals?
Almost all the thinner.
Yeah, yep, all the thinners. Does anybody use any methylene chloride or acetone, toluene, xylene? Any of that stuff? It's going to have very high vapor pressures. It's going to be very, very volatile. Which, by the way, let me back up here. So I've got these vapor pressures here, and we've got a rule of thumb about if something is considered volatile or not in concern to health and safety. So chemicals that have a vapor pressure of 10 millimeters of mercury or more, we're going to consider those volatile. They're going to readily get up into the air once they're uncapped, once they're out of their container, and it's going to cause an issue for workers. If it's got a vapor pressure between 1 and 10 millimeters of mercury, we consider that to be a medium vapor hazard. And if it's less than 1, we consider that to be a low vapor hazard. Again, doesn't mean that there's no hazard there. It's just unlikely in room temperature conditions that it's going to get up into the air and cause trouble for workers, breathing and respiration, or affect their eyes or skin, something like that, unless it was dispersed in some way. All right, sublimation, I mentioned that back on that little diagram. It's the ability of a material to change from a solid to a gas or vapor without becoming a liquid, right? So instead of, water going from a cube of ice back to liquid water to water vapor, right? That's an example of not sublimation. Can you think of any solids that can sublimate?
Dry ice?
Yeah, dry ice, and that's what I have a picture of here, right? So dry ice, they use it a lot in movie making and things like that, right? Because it's what is dry ice?
Liquid carbon dioxide.
Yeah, that's right.
Solid carbon dioxide.
Yes, it's solid carbon dioxide. This is one of the things that they're trying to use to keep our vaccines cool as they're transferring them to stationary refrigeration units. So it's frozen dry ice, and it's negative 76 degrees Fahrenheit. So that is cold. If you touch that with your skin, you'll feel it. So that's cold. So this sublimates. It'll go right to carbon dioxide gas if you let it sit out in room temperature. Volatile chemicals readily evaporate at 70 degrees Fahrenheit and atmospheric pressure, which is 760 millimeters of mercury. They're going to have low boiling points, right? So in other words, it's not going to take a lot of heat to get these things to boil. So they've got low boiling points. And their vapor pressures are the opposite. They're going to have higher vapor pressures. The closer something gets to 760 millimeters of mercury, the closer it behaves and acts like a gas. So if you have a liquid with a vapor pressure of 720 millimeters of mercury, it's right on the line of being a gas. So, I mean, it's going to get up in the air immediately, right? If you expose it to the atmosphere. And again, this is important stuff because, it can change your behavior, how you might work with certain chemicals, right? Maybe if you're mixing something that has a very high vapor pressure, maybe you decide to do it with some kind of ventilation or outdoors. You do your mixing of it and then you bring it in where you're going to work. So we can change things up like this. And that's an example of implementing that hierarchy of controls, right? So we're just not relying on respirators, but you're changing either the work process or maybe using engineering controls or eliminating a hazard before you have to jump down to a respirator. And the problem with some of this stuff that we use as IUPAT members is it's not just going to be a respirator hazard, right? Or an eye irritant if it gets up in the air. What else could it do? Almost every chemical that I've looked at that an IUPAT member uses has this in common. Not everyone.
Toxic.
What's that?
They're toxic.
They're toxic, yep. But I'm looking for a different hazard. Boom, flammable. A lot of these things that our members use are flammable. And so in addition to not wanting to breathe them in or touch our skin or eyes, we don't want to have them get up into the environment to such a degree where it's going to create a source of fuel. And we're going to get into that. So understanding the volatility of these things is important. Speaking of which, flames. So this is the fire tetrahedron. Up until the late 90s, it was called the fire triangle, but the NFPA, the National Fire Protection Association, changed it to a tetrahedron. What they did is they added, in addition to oxygen, heat, and fuel, the leg of chain reaction. The reason why is if you take away any one of these three things up here, you're going to break the chain reaction. And you need these three things to have a fire. So for instance, what happens when you put water on like a wood fire? What is that taking away?
Heat?
Heat, yeah. Water is the world's greatest heat sink. That's one of the reasons why it's tough going swimming in a cold lake, right? Or New England waters at the end of the summer. It sucks the heat right out of you. How about if I had, let's say if I had toluene and that was on fire, or we're going to hit that with foam, what is that going to do?
Take away the oxygen.
Yeah, that's right. It's going to smother it. It's going to take away the oxygen. So by doing that, we break the chain reaction. So that's why we've got this fire tetrahedron, which is a requirement for fires to be produced. And as I mentioned before, my firefighter examples, if you've got a fire, it's an uncontrolled chemistry experiment, right? Because everything in there is on fire. It's changing its chemical makeup. It's combining, making new chemicals, degrading chemicals, all at the same time. Flashpoint, very important to understand, especially if you're working with some of the stuff in an enclosed or confined space. Now, why do I keep differentiating between enclosed and confined space? Does anybody know why I'm using those two different words and why they're different?
Properties of a confined space are it's not habitable, limited access, and what's the other one?
Not for human occupancy.
Yep. Not for human occupancy and large enough for a person to get in, right? But
yeah, anything could be an enclosed space.
what's that?
You could have anything could be an enclosed space, even with doors, if the doors are shut.
Exactly. So you might have like a small room or a chamber or something like that. And because there's a big door there, OSHA wouldn't define it as a confined space. But if you're using a volatile chemical in there, your likelihood of having that chemical being affected and increase its potential for harming that worker could be just as bad in an enclosed space, even though OSHA doesn't define it as a confined space. And because of that, there's no permit required, right? So this is something to be cognizant as when you're teaching this stuff, or if you're doing, health and safety rep kind of work. What kind of places are your members working in? Just because it's not a confined space doesn't mean it's not going to be trouble if they're using, chemicals. So let's look at flash point. So this is the minimum temperature at which a liquid gives off vapor in sufficient concentration to form an ignitable mixture near the surface of the liquid. So it's not the actual liquid that's on fire, right? The thing that's actually burning is the vapor right above that liquid material. And it's the same thing for solids. So, if this solid paper book was on fire, it's not the actual paper material. It's all the vapors that were heated up right above the surface of this that are on fire. Have you ever heard the term flashover? A flashover is that event, that point of an event where a whole room just bursts into flame. Now, what causes that? So there's a fire somewhere, or there's heat introduced into that room where it's heating up all the solids, all the liquids in there. And it's giving off vapor, and gases, which are flammable. And at some point with ignition, it all catches on fire and you have this big ball of fire happen in the room. It's not an explosion, it's a flashover. And then all that vapor gets used up. And then what happens is you've got a sustained fire in most cases, because the stuff there now is under ignition and it's giving off its own fuel source now in the form of vapor, which is constantly on fire. And that fire aids that process. So unless you're gonna, cut that chain reaction, you got your fire going. So a flash point is important to understand. So chemicals are going to have different flash points, and when you look them up, they're going to be a concern. If you see a chemical that has a flash point next to it, that should be important information as far as planning that work. And it could be important depending upon where you're working. So let's say if you're working in Buffalo, New York during the winter, and you spill some toluene outside. Matt, give me an average temperature for Buffalo wintertime.
Wintertime?
Yeah.
About 25 degrees.
25 degrees. So the flash point of toluene is 40 degrees Fahrenheit. So if you spill that in Buffalo in the winter on your average day, probably not going to have to worry about a fire hazard right away with that stuff. I would still be cautious in cleaning it up and et cetera, but that wouldn't be first on my mind. However, what if you are down in Arizona in the summertime? And I don't know if we have anybody from down that area in the class today, but could temperatures conceivably be 100 degrees Fahrenheit, 105, 110?
Yep.
I know I've seen shows where people fry an egg down there on a metal surface some summers. So that would be much different if I spilled toluene in the summer in Arizona. That then would change the order of how I would react, to a spill like that. I'd be thinking, oh gosh, there better not be an ignition source around here. So these are, some examples of how we apply this stuff to look at protecting workers. And so do you do this, on the day of the job? Do you apply this information on the day of the job and come up with it?
No, pre-planning.
Right. This is why we want to do this work before. That's why it's important for employers to conduct job hazard and job safety analysis. And that's important for workers to be part of that. Nobody knows the work better than a worker. And so it's really important that they are allowed to participate. And as a bargaining unit member, we are, to be a part of that process because they might be using a chemical in a way that, that supervisor or the manager has they couldn't conceive, right? Or the industrial hygienist. There's a lot of industrial hygienists I know that don't interact with workers that they're trying to protect, which is bluntly stupid to me. I mean, unless you're going to involve the workers doing the work, I don't know all those jobs. Anyway, so that's important to consider. You want to be able to get this stuff done ahead of time. And ask the health and safety professionals on site, hey, have you done a JHA with these chemicals we're using? Flammable limits. So lower explosive limit is the minimum concentration of a vapor which is going to burn in air. So you've got enough fuel, in other words, for a fire to occur. And the upper explosive limit is the maximum amount of vapor in air for a fire to occur. If you've got something over that, it's going to be too fuel rich, you won't have a fire. And the flammable range is that sweet spot in the middle of those two values. So this is what it looks like on a graph. So, I just gave some numbers down here from 0 to 100% concentration of a vapor, any vapor in air. So wherever the LEL and the UEL of those chemicals are, we've got anything below the LEL is too lean, anything above is too rich. And right in the middle, that's the good spot. Or I should say that's the spot you don't want to be. So, you don't have to worry as much about a fire if you're down here, but can the concentration of vapors in air change at a moment's notice and go from too lean to flammable range?
Yep.
Can you think of any work situations where that could occur?
Yeah, any confined or enclosed space.
Right, that's right. I mean, I'm just thinking about, inside tank work or something, right? Or, working on boats or submarines, coating, things like that. That could change really quick. And then the same thing for too rich. I mean, you might not have to worry about a flame up here, but, one of the issues is, one, it's going to be so damn toxic if you're not protected, for respiration in your skin. Your body's going to melt from the chemical. But if you all of a sudden introduce ventilation into that area, you're going to have that concentration fly down, and it's going to go through that flammable range. And if you happen to have an ignition source, you could have a fire. One of the reasons why firefighters are always nervous about, going to a home that had a natural gas leak where all the windows were closed and then opening them up. Because if they're not careful, if they haven't, snuffed out all of the ignition sources, they're going to be bringing that environment from a potentially too fuel-rich environment through that flammable range as they're ventilating it out through opening up windows and doors. These are just some different examples of flammable ranges that can, vary widely. A gasoline is 1.5 to 7.6. And we've got something like acetylene, which has got a humongous flammable range, 2.5 to 100%. So this is a giant flammable range. Any comments or questions? All right, now let's throw some of this stuff together and go through this little activity. So what would make a chemical really flammable? So this is a neat little activity to kind of spark our brains to think about risk when we're looking at flammability chemicals that we might be working with. So what would make this chemical really flammable? Having a lower or a small flash point, or a higher or large flash point? Which would make it more flammable?
Lower.
Low.
Right, good. How about vapor pressure? Would a lower vapor pressure make it more of a flammable risk, or a higher one?
Higher vapor pressure.
Very good. How about LEL? Would you rather have a small or low range, or a wide or large range? What would make that more flammable risk?
Wide.
Wide, right. Oh, that is backwards. That should be changed. So my X should be over here. So a higher range is going to make that more of a concern. How about, oh, wait a minute. I did this last time I taught the class. This is funny. I'm going to say, maybe I'm just zoomed out. So I had it right. How about LEL? Let's go back for a moment. Would a lower LEL or higher LEL make it more flammable?
A low LEL.
Yeah, that's right. So if my LEL was 1% as opposed to 20%, that would make it a lot more flammable. And you already answered the flammable range one, higher. So if I've got a narrow flammable range, my risk or my chance of being in there is, well, it's narrow, just like that flammable range is. But if it's wide, like acetylene, 2.5% to 100%, I got to be really careful, because almost anything that I get up into the air around me is going to be a flammable range, right? So if you do this little check for chemicals that you work with, you can determine if it's going to be a fire risk for those workers. Reactivity is the potential for a material to release energy either by itself or when it contacts something else. And when that happens, you can cause a fire, you can have an explosion, release of toxic chemicals. Does anybody have an example of any flammable, reactive chemicals that they either work around or that they might have information on? Does anybody own any pools?
Yes.
What's that chemical with that yellow diamond on it?
Oh, chlorine.
Yeah. The oxidizer. Right. So oxidizers are going to react pretty aggressively. They're reactive with water. How about acids and bases?
Oh, yeah.
Those are pretty reactive. Do IUPA team members work with acids or bases at all?
Of course.
Yeah, and you can affect the reactivity depending upon how you mix them together. There's an old chemistry saying, do what you oughta, add acid to water. Because if you add water to acid, it's gonna create so much energy that you're gonna have a sputtering of acid droplets. That's why you wanna add acid to water little by little, as opposed to the other way around, that water is gonna act as a energy sink and dissipate the energy so it won't sputter up and splatter. And you can find information about chemicals if they're reactive, and it's important because if you're using something and you don't know it's reactive and you happen to use it with the wrong stuff, you could have a bad event occur. We have corrosivity, so pH describes the acidity or alkalinity, of a liquid. So things that are less than 7, it's acidic. If it's 7, neutral, and greater than 7, it's basic. And pH is an aqueous measure in water. So basically it's the percent free hydrogen ions, if you want to think of it that way, in water. So the more hydrogen ions that are there to be used up, the more acidic something is. And whether it's acidic or basic, it can damage your tissue, especially, more sensitive tissues like your eyes. It can cause corrosion, things like that. It can deteriorate materials. These are just a couple examples on the pH scale of some of the stuff that we've got in everyday life. Battery acid, it's very acidic. It's around 1. Lemon juice and vinegar, we use these things in eating, right? Adult fish dye at pH of between 3 and 4. And then up here, we got things like ammonia, pH of 12. Milk of magnesia, something that we might use to buffer our sore stomachs if we've had, too much pepperoni pizza with habanero peppers on it. I don't know. Then we got specific gravity. This is a measure of how dense something is compared to water. So we're going to use 1 as an example of water, and that's what we're going to compare it to. So things that are less, it's going to float. If it's greater than 1, it's going to sink. And if it's the same as water, it's going to sort of suspend and mix in with water. This is more important if we're talking about, environmental protection and contamination, things like that. So, if you're working with material and it happens to be, a high specific gravity and you're working around water and you spill it in a river or, a lake or something, it's going to sink down to the bottom. It's going to be harder to clean up because you got to dredge that. You got to take that material off of the bottom, vacuum it up. If it's lighter than water, it'll float and you can get that off and clean that up a little bit easier. And if it's got a specific gravity close to 1, it's going to make it a little more difficult as well because it's suspended throughout that liquid. What do you think this chemical has for a specific gravity? Is that less than or greater than 1?
Less than.
Yep, less than. That's a good old oil slick. Vapor density, this is another thing that is very important for worker health and safety, and also relative gas density. It's the weight of vapor compared to the equal volume of air at atmospheric pressure. And again, we're going to use 1, right, for air. So if a density is less than 1, it means that it's going to rise. If it's greater than 1, it means it's going to sink. Now, why do you think vapor density would be so important to understand about chemicals concerning worker health and safety?
To know where it's at as opposed to your position.
Good. Do you have any specific examples of maybe some work environments that this could really play an important role in?
Confined spaces.
Yeah. Yep. Confined spaces, including trenches or pits, or enclosed spaces. And sometimes vapors can be so dense, they can travel through floors. I mean, you can cause a public disturbance if you're working with a certain chemical, say on a 5th floor, and you don't account for, it being vapor dense. For instance, toluene, you mentioned that. I know that it's a chemical that IUPA team members use. I can go and buy it in gallons at Home Depot. Its vapor density is 3.6. And I can tell you from experience, from industrial hygiene investigation, if you were to release that on an upper floor whether it be a 5th, 6th, 7th floor, you're gonna detect that on the bottom floor within an hour. It's a very dense material and it's got a unique smell. So it's important to understand kind of the density of the stuff you're working with. Now, in the pocket guide, RgasD for gases is going to be listed, but vapor density is not. And this is how you calculate it. What you're going to do is take the molecular weight of the chemical that you're concerned about, and that is in the pocket guide. So why don't we look up the molecular weight for toluene if you happen to have a pocket guide near you. I think it's 90 something.
Yeah, 92.1.
Okay, great. 93.1. So you would put that in the numerator up here, and then you would just divide it by 29, which is air. And, for most cases, unless you're, going to be deep in the ocean or you're going to be up on top of, Mount Fuji, it's going to be 29. So, you take that for toluene, you put it up there, divide it by air, you get 3.1. Okay, so I said 3.6 the first time I was off a bit, but it's around 3. So this is really heavy. And you're going to have to do this for any liquid that you've got because it's not going to tell you the vapor density in here. Now, it might state it on a safety data sheet. It should, but you're not guaranteed that. So you might have to do this yourself. Solubility is the ability for a solid, liquid, or gas to mix with water or dissolve in water. Just like if you add salt or sugar to water, it's going to dissolve. However, at some point, you won't be able to dissolve anymore, right? That's because that space between the molecules of water is going to be full. However, we can fudge that a bit by doing what?
Eating it?
Yeah, eating it. That's right. Adding heat to that. Absolutely. So here's an example. Solubility, gasoline and water is not soluble in water. MEK, on the other hand, which is something that methyl ethyl ketone, right? Painters, IUPAT team members might use this stuff. It is soluble in water. Miscible versus immiscible. So, miscible, it's going to mix in any amount, and immiscible, it's not going to mix regardless of the quantities that you put in, whether it be a tiny bit, or a small amount. Viscosity, the resistance of a liquid to flow. So generally, the thicker the liquid is, the more viscous it is. And again, these are probably some of you've probably experienced these, just in your everyday work as a painter, right? Do you have to apply your craft differently if it's 10 degrees out versus 100 degrees out?
Yep.
How about, Mr. Russo is telling this to me about Orlando, about the humidity. So there's certain times in the day where they can't go and paint outside, I guess, because that humidity is going to affect what happens when they put, coatings on surfaces. So these are all things that you've probably used right along, right? So viscosity, here I got an example of water. It flows a little bit more freely than oil, engine oil, and that frees more freely than honey. And it's affected by temperature. So more viscous stuff is going to be harder to clean up, harder to get off of surfaces, etc. Any comments or questions before we finish up with radiation? Okay. So radiation is the property of certain atoms to emit particles, electromagnetic wave energy, or both simultaneously. You might have heard the term photon. Sometimes they use that, photon radiation. So it's basically an electromagnetic wave and particles working together to produce this energy. And energy in motion is another way that we describe radiation. Again, if you work on a Department of Energy site, if you work at a university, hospital, research facility, likely you're going to find radiological sources there. If you work in the shipbuilding industry, you're likely to find radiation sources there. The Department of Defense, same thing. And even in construction, we do have a couple of instruments that use radiological sources. This is the old trifoil symbol for radiation. We don't use this anymore. This is the new one that we use. It's going to be this triangle that's red, and it's got a couple pictograms here telling you to get the hell out of there if you see this stuff. There's 4 types of ionizing radiation. So I'm only talking about the kind of radiation that has enough energy to strip electrons off of atoms. So we call that ionizing radiation. And I'm going to get into this stuff really deeply and talk about its effects on workers when I teach those other 2 courses I mentioned. But we've got alpha, beta, gamma, and neutron. Which one of these, by the way, made the Hulk? Pop question.
Gamma.
Yeah. Gamma radiation. Which one of these is the most damaging to our body as far as health effects is concerned? And it's one that a lot of us have to worry about, depending upon where you live.
Beta?
No,
No.
alpha. Alpha. Anybody here live in New England or New York, especially upstate New York? There's this little thing called radon, and it's not just New England and upper US. It depending upon what kind of bedrock you have your home built above. Radon. So radon is a radionuclide decay product of uranium, and it's incredibly hazardous to our lungs. Radon, or alpha radiation, is the 2nd leading cause of lung cancer in adults, right next to cigarettes. It is debilitating. There's no law requiring how much you can have in your house, but the EPA does have a guideline of 4 picocuries, which is a unit of intensity measurement for radiation, 4 picocuries per liter of air. If you have that, they highly recommend that you control that high radon source in your house. And I'll talk about this more in that other class, but it is really important as a public health issue for you and your family to know if you live in an area that has high radon. And EPA has a map that you can go on and look on EPA's radon map. But these other ones here also cause damage, but not in the same way or to the same extent. And we'll talk about a little bit of these before we end the class and get into our activity. I'm not going to mention neutron too much. Yeah.
Power lines, don't they produce a lot of radon? I thought I'd heard that before.
No, so power line, very good question. So power lines produce electromagnetic waves, and electromagnetic waves are a type of radiation. There's not enough research to show that it can cause cancer. However, we have a number of studies that show cancer clusters around homes that are near high tension power lines. So the real big power lines that move a lot of energy through. Those electromagnetic waves, or EMFs, are a lot higher. So we don't have enough study on those yet. It looks like they can cause cancer. I had when I bought my last house, when we were looking to move, it was a house I didn't have to do anything to. It was beautiful. I didn't have to update anything, paint anything, knock out any walls, nothing. I could have just moved in. But it happened to be within 25 yards of a high tension line. I said, no, we can't do it. So we didn't. So I bought another fixer-upper. I bought a house that was built in '76. Looks like the Brady Bunch, but hey, it was cheap. How many people here ever had chocolate brown and sky blue bathroom fixture? Anyway, so yeah, so that's a good question, and those can cause some damage, we think. But unfortunately, science and policymakers are really bad at getting together and deciding at what point should we say something is damaging to a human, and then implement a rule about it or a protective measure. So if you are working around that stuff, it's not a bad idea to look at, protective measures and things like that. And power lines, they're actually going to oscillate their electromagnetic waves on demand. So let's say if you are working around high tension lines in the summertime, that's going to be worse because people got their ACs on, it's drawing more current, the EMFs are going to be higher. as opposed to like, you know, in the fall or the winter or something like that. Anyway, good question. I got off from ionizing radiation a bit, but I'm always happy to take those things. So thank you.
Thank you.
So this is again, the most damaging one, the one that we really need to protect workers against. Luckily, it's an easy one to protect workers against. So alpha radiation, it's a particle that contains 2 protons and 2 neutrons. And I get into this in my other course, but it's fairly large, heavy, as far as a tiny microscopic particle is concerned. It has a +2 charge, and that's one of the reasons it's so damaging when it gets inside our body, because that +2 charge likes negative charges. So it strips electrons from our cells, from our DNA, from our RNA, from our cell material, because it's pretty strong. And things like to be neutral. Things don't want to walk around in our body with a +2 charge. It wants to be neutral. So it's going to rip things away from our cells. It doesn't travel very far. So if this phone was alpha radiation source, it would the radiation would only travel a couple inches above its surface. Now, why is radon so deadly if it doesn't travel that far? Well, it does, because it behaves like a gas. So those radon particles float around on the currents that are in our basement and our houses. So that's how it can get to us. And so then if we inhale that stuff and it gets deposited in our lungs, it only needs to travel a 16th of 32nd of an inch, and it's going to cause its damage. But luckily, if it's stationary, it doesn't travel very far unless it gets disturbed. It's going to deposit a large amount of energy in that short distance of travel. So that's another reason why it's so damaging to our tissue. If it gets inside of our body, that small amount that energy and motion is going to travel is going to cause a lot of havoc. And we consider it an internal hazard, because what is going to stop it is intact skin. A sheet of paper will stop it. And then once you get up to, plastic or heavy material, you don't need to worry about it, because paper will stop it. And in the radiological worker course that I teach, which is a 24-hour class, I have all these hands-on activities that we do with safe and closed radioactive sources, where we actually block the radiation with different types of materials. And you can see that alpha radiation is blocked pretty easily. And then we have beta radiation, which travels a little bit farther. It can go up to 20 feet. So by that, I mean, if this was a beta radiation source, I would be able to detect its energy 20 feet or so away. Now, depending upon what the source is, it might be a little farther than 20 feet. It might be a little less. But if it was alpha radiation, I would have to be within an inch or so of the surface to detect that energy. So if I'm farther away from the alpha source, I'm not going to worry about it, because that energy is not going to reach me. So these are some of the concepts of radiation that make its understanding a little bit more unique. So we have to do a good job when we're developing material and talking about it so that students can understand it. Just because that alpha radiation has a lot of energy, it only travels a short distance. So if I'm 5 feet away from it, I'm fine. But if it's dispersed up in the air, floats around, and I inhale it, I'm in big trouble. Beta radiation, however, can travel a little farther. So if something's 10 feet away from me, that energy is going to reach me, and it's strong enough to actually penetrate into my skin by a few millimeters. So it's an external hazard. It can also be an internal hazard if beta particles got inside of my body. And this stuff can be stopped with some plastic or lightweight metal. It can go into skin, okay? Next, we've got gamma radiation and X-rays. They're very similar types of electromagnetic radiation, and they're really close to each other on the electromagnetic scale. And yes, it made the Hulk. What made the She-Hulk? This is a deep pop question.
It was his blood, wasn't it?
Yeah, man, who said that?
That's Brandon.
All right, we're gonna have a good time when we get together. Let me tell you, couple of beers.
Yep, looking forward to it.
Oh yeah, that's right. It was a blood transfusion from the Hulk. So Bruce Banner had to save his cousin, and then she became the She-Hulk. So this stuff travels a very, very long distance, hundreds of feet, up to miles. It doesn't have any mass or charge. So it basically has no weight. The range is incredibly far, as I said. The penetrating power is very high. So this can go through your skin, it can go through drywall, it can go through wood, go through plastic. We consider this a whole body exposure, and the hazard can be external or internal. And again, this stuff, if you're near gamma radiation, it's going to fry you, right? But it's not going to cause as much damage for the same activity or the same intensity as alpha radiation, if that alpha radiation got into your body. To stop this stuff, though, you're going to need something like lead or multiple feet of concrete to be able to stop gamma radiation. Now, the thing with radiological materials is that they give off all three of these types of radiation, for the most part, all at the same time, but in different amounts. So, like uranium is going to decay to a different atom, and it's going to give off a large amount of gamma radiation, a little bit of beta radiation, and very not much of alpha, for instance. If you had a nuclear detonation, like you dropped a bomb, all three forms of radiation are happening at the same time, and they're all going to be spread out and dispersed and get out into the atmosphere all at the same time. So you usually don't just get hit with one of them, but you're primarily going to be affected by one more than the others, depending upon what that radiation source is, or more, the better way to say it is what that radiological source is. And again, neutron stuff, I'm not going to touch too much on. We basically capture these things in it's up in Canada somewhere in the deepest lake in North America. Okay, so I never can remember the name of it, but there's a research center where they can actually catch neutrinos, neutron radiation at the bottom of this lake. They have to use all that water to slow it down, remove some of its energy so they can actually capture and detect a neutron radiation. This is basically cosmic radiation. It's very difficult to stop. You can't detect this stuff by smelling it, seeing it, right? So we have to, if you're going to be around it, you have to have a detection method to actually do it. So we've got an example here of a radiological detection meter here, a Geiger counter. This is an example of a pen dosimeter. So if you're working around it, we want to make sure that you're not getting a certain amount of radiation above what the legal dose is. So I know a lot about health physics because I've done a lot of work on DOE sites, and it's kind of a fun thing for me to to get into. But unfortunately, the old Department of Energy 5 rem per year worker dose is probably way too high. We've got a lot of new research that shows that there's an immediate dose response at very low levels of radiation, and that just increases the more dose you get into your body. And we can talk about this more in another class, but it's very important if you're working around this stuff that you're measuring how much of a dose you're getting to your body. And this has to be set up by an employer. If you're working around this stuff, they will have a health physicist that's going to be responsible for worker protection, health physics protection, et cetera. All right, any comments or questions? We covered all the stuff that I wanted to. Hopefully, we had enough examples and discussion about how this stuff directly relates to worker protection. What I want to do now, if there's no question, we're going to get into the activity. So what we're going to do is we're going to look at the pocket guide here. I'm just going to go through it briefly. And then in that manual that I sent you, we've got a group activity at the very end. And we'll just spend a few minutes. Nicole can split us up into, how many people do we end up getting, Nicole?
Like 10. We're
10.
good. Yeah.
So we can split them up into 5 and 5. We'll do two groups. All right, so this is an IASH pocket guide. It's got 677 chemicals are represented in here. This is by no means all the chemicals out there. For those of you who took, the toxicology class that I did, we learned that there are 100,000 plus chemicals that are used out in the world. There are, I don't know what it's up to now, 80 million known chemicals that are registered and that have a CAS number. And we discover 10 to 15,000 new ones every year. So this certainly does not represent all the chemicals out there, but it represents most of the stuff that we might come into for workers, right, that are used. And it's got a lot of great information. So we're just going to go through it. It's set up in alphabetical order, but for those of you who know about the pocket guide, if we have a synonym or trade name, that might be listed in the very back of one of the appendices, and that will refer you to a different page in the book. So an example there always is, I think it's MEK. MEK is not listed as methyl ethyl ketone in the book. You have to go to the back, look that up in the appendice, then it tells you to go to a different page. That's not in alphabetical order for MEK. So these are the things we've got. We have a formula here. So it's going to tell us what the chemical formula is. This is hydrogen fluoride or hydrofluoric acid, or HF. I don't know if you've ever worked around this stuff, but it's incredibly nasty. We've got the CAS number, the chemical abstract service number. This is like a fingerprint. So every chemical that's discovered and named has its own CAS number. Then this is a number out of NIOSH. Oh boy, it's a registration number for toxic chemicals. I always forget what this acronym is. Look the sucker up.
Bernie, how long you want the breakout rooms to last for?
Let's see, why don't we go, what time is it?
3:20.
We can do 15 minutes.
Okay.
Here we go. NIOSH's Registry of Toxic Effects of Chemical Substances number. So NIOSH assigns an identification number to chemicals that they have researched and investigated. This here is our IDLH, right? So this is a really important value to know for selecting what?
Respirators.
Respirators, all right. Conversion, so if you want to go from parts per million to milligrams per cubic meter or backwards. We've got DOT. Oh, I don't have a pocket guide in front of me, do I? No, I don't. All right, so you know that little orange North American emergency response guide? It'll also state what the UNID number is, what the guide number is, for this stuff. Here's our synonyms and trade names. So I call this hydrofluoric acid, but up here in its alphabetical title, it's hydrogen fluoride, but they call it some other things here as well. Then we've got exposure limits. We're going to have the NIOSH ones in OSHA. Physical description, so what it looks like, what phase it's typically going to be found in. Measurement methods. What does this box here tell us? That's a really important one for me. This here tells us what analytical method and what sampling method I have to use to collect a personal sample on a worker to be compliant. So if I'm concerned about finding out if an employer is in compliance, if they're overexposing workers, et cetera, I have to make sure that I look up the correct sampling method and that I abide by that to make sure that I'm taking a valid sample. Chemical and physical properties. So a lot of the stuff that we covered, molecular weight, boiling point, solubility, it's going to list these things over here. And again, you'll notice that, they're not going to have vapor density. This is a liquid. And we notice here, it's got a vapor pressure. So this is 783 millimeters of mercury. So what does this tell us? Remember, I talked about if there's a certain value for vapor pressure that a chemical has, it's going to be very telling. What is atmospheric vapor pressure in millimeters of mercury? Remember back to that slide.
Was that the 29?
What's that, Dave?
Was that the 29 that you were talking?
Yeah, yeah. So it was 29, but for that was 29. What is 29? PS? No, if it's 14.7 psi, Oh, 29 is the molecular weight of air, right? So that's how we find vapor density. But if we're talking about vapor pressure, remember I said that 760 millimeters of mercury is equal to 1 atmosphere, is equal to 14.7 PSI. That's atmospheric vapor pressure. So if you have a chemical that has a vapor pressure above that, it's a gas. So look what we have here. Hydrogen fluoride is 783 millimeters of mercury. That means that this is in a gaseous state. So this is going to come shipped, right, in a cylinder, right, or it's going to be a compressed liquid. So this is important to know because, you know, if this gets out, you're not going to put it back in the bottle, right? And this can disperse very quickly. If somebody's working with this stuff, it could be in a large room and it gets out. People working on the other side of the room are going to experience the vapors quite quickly. But you'll notice, back to your point, Dave, the 29, the molecular weight of air, so this has a vapor pressure. It means that it can volatilize. There's no vapor density. So I'm going to have to calculate this myself. So how would we do that again?
Divide the 20 by the 29 and you'll find that it's very light. It's going to be
Yep.
way up high.
Yep, that's right. Which is another problem if somebody on the other side of the room release this stuff, because the lighter it is, the faster it's going to dissipate around the room. If it's heavy, it's going to take longer to get out and stretch out into that room. But if it's lighter, it's going to mix faster. So very good, excellent. Personal protective and sanitation guideline here. Here we've got respirator recommendations from NIOSH. Other things the pocket guide will have: incompatibles and reactives. This is really good. You know, so if you spill this stuff on metal, if you spill it in water, you know, it's going to cause a bad event. Exposure routes, symptoms, and target organs. So for those folks who might have been in the toxicology class that I did, if you remember back, exposure routes are how we get it into our body. A target organ is that organ in your body that the chemical loves. And we can see here bone. So, you know, you might have heard the phrase that hydrogen fluoride or HF is a bone seeker. It'll actually go right through your skin. It's gonna marry up to that skeletal system you got. And then first aid measures in case you get exposed to it. So that's our pocket guide. There's a lot of stuff here, a lot of good information. I can use this for the most part to quickly look at chemicals, and I can do a rough risk assessment, and I can say, yeah, no, we're not going to worry about this one too much, or, oh, hold on a minute, we better put some protective measures in and figure out exactly how people are going to be working with this stuff, because it's pretty dangerous. All right, any comments or questions about what we covered? All right, so what we're going to do, we've got this activity here, and we're going to have Nicole split us up into 2 groups for 15 minutes. And what you're going to see is, you know, there's a table here with a bunch of chemicals on it. So Nicole, when you select group one, if you could do asbestos and MEK, and then group 2, if you could look up cadmium and toluene and find that information. And then what I'd like you to do is answer questions 1 through 4. And the group activity, you know, has an example of a pocket guide, but you're going to have to use your own pocket guide or you know, electronic pocket guide. So with that said, Nicole, if you want to split them up, again, group 1, you're going to do asbestos and MEK, and group 2, you're going to do cadmium and toluene.
All right, we'll see you guys in 15 minutes.
Thank you, Nicole. Sounds good. All right, everybody, welcome back. All right, so you know, for the training aspect, if actually, do we have everybody back, Nicole? Yeah. So, you know, for a training aspect, let's say if I had, you know, 20 people in class or something like that, I would try to mix up the groups, right? I have a bunch of different small groups, and I would probably ask, depending upon how the time went on teaching this, I would either split it up and just assign a couple chemicals to each group, or I could say, hey, every group you're going to do all of these and split them up amongst yourselves. And then I would go back and debrief them, you know, 1 group at a time or something like that. The other thing you'll notice is on the table, I have a couple blank spaces. I have never done a class where somebody has not asked me if they could look up a chemical that they work with. Yes, of course. That's exactly what we wanted to lead participants through by the end of this class, right? So, mention that, this blank space and say, hey, if you work with a particular chemical, check it out, look it up, you put that down there and do that as well. So what I wanted to do is, I'm not going to go through and ask all the values for the table and stuff, but I'll just ask it generally. Did anybody have any problems looking up either the CAS number, the form, vapor pressure, molecular weight, LEL, or flash point? Did everybody find everything okay? Yeah, okay, good. How about for any of the chemicals? Does any of the chemicals that you looked up present a fire or explosion hazard?
Toluene, that's got a fire.
Yep. Any of the other ones?
MEK.
Yep, MEK, those two do, definitely. Is the chemical likely to form high vapor concentrations?
Toluene, yes.
Yep, how about MEK?
Yes.
Yep, remember I mentioned 10 millimeters of mercury. So if you hit that or above, you got to consider that a high vapor pressure. Number 3, is a vapor gas lighter or heavier than air?
Toluene was heavier,
Yep,
as well as cadmium.
yep. Yeah, and cadmium is a solid, so cadmium is best is definitely heavier than air. How about the MEK?
It's heavier.
Heavier, okay, good. Let's see, do you have any other concerns about the chemicals?
Yeah, the physical aspects of both of ours, toluene and cadmium,
Yep,
target organs.
yep, target organs. Now, anything particularly of interest with asbestos or cadmium? Health-wise?
Well, asbestos is a carcinogen.
Yep,
So we put down, for any other concerns about the chemical, we had selected carcinogen, avoid inhalation, skin contact, and PPE required.
good, good. And cadmium is a carcinogen as well, and it's also a reproductive hazard. So cadmium's pretty nasty. And again, I've done a lot of study on cadmium where I've gone into facilities that use cadmium coated fasteners in hardware because it's great aversion to corrosion. It doesn't rust. I was in a Bradley M1 fighting vehicle factory that was refurbishing stuff that came back from the Persian Gulf. And they had to strip out all the hardware, clean everything down, put them back together, and put it back out. And there was a significant cadmium overexposures. And this was a union shop. I went out and I did this job for a sister union. And the employer didn't have a cadmium. First thing I asked for is I said, can I see your cadmium program? They said, what's that? Come on, you guys got this DOD contract and you don't have a cadmium program. Significant stuff. One of the members, unfortunately, had some issues with conceiving, and it was thought that it was because of their high cadmium body burden that they had inside of them. So, some of the stuff's particularly nasty. And in the toxicology class, we did the sister table of this where we looked up health effects and stuff like that. But that's exactly what you want to do. You want to, get the physical and chemical properties down. You want to look for any, found or determined health effects, health issues with this stuff. And from there, you can make a basic risk assessment of that chemical. And if you need to look into it a little bit more, how they're going to use it. I mean, for instance, I'd have problems if people were using MEK or toluene in confined space, right? I would say, hey, based on you taking that in there, Mr. Employer, I think your workers are going in a permit required confined space now. Are they trained for that? Do you have a permit required confined space program? So it can open up, a lot of health and safety issues and avenues of controls just by doing a simple activity like this. That's it. Any comments or questions about the course? Anything you'd like to add or discuss?
You can pretty much find all this stuff on the safety data sheet, right? For the product you're using.
Yeah, for the most part, this stuff's supposed to be identified. As you probably know, there was a better quality control, right? Once we moved from material safety data sheets to SDSs under the GHS HASCOM standard of 2012, but they're not perfect. You still might not find some of this stuff. And one of the issues is, you know, if it's a mixture that you have an SDS sheet for, they might not list the individual components, chemical and physical properties. So you might not have the vapor pressures for all 5 chemical ingredients, and you would want to know that, you know. Yeah, I mean, I'll tell you, it's the IUPAT is a unique union because there are so many chemicals that members potentially touch in their jobs every day, you know, for every branch. Every field. It's amazing. So hopefully this is some, you know, information that'll help you not just in your training, but if you do any, like I said, health and safety rep type work for your local unions or district councils. I'll just plug again about the survey form at the end. I really do look at those, and if you've got any comments or questions, anything that you'd like to see improved on the class, you know, I always look for that stuff to make sure that we can, you know, get the word of the members in there. So with that said, if there aren't any other comments or questions, thank you all for spending a few hours with me here on this fairly sunny and fairly cold New Hampshire afternoon.
Thank you, Bernie.
Yeah,
Thanks,
thank you all. Eric, I hope to see you soon. Hope to come and visit soon.
You're always welcome up there, Bernie. You know that.
Thank you. It's only 45 minutes away, but in the pandemic, it feels like a world away.
Yeah, no kidding.
Yeah. Yeah, I still got to get sworn in and all that stuff too. So
We'll get
looking
you.
forward to it.
We'll get you.
Yeah. All right, everybody. Thank you all.
All right, guys.
Thank you.
See ya.
Bye-bye.
Benny.
Bye.